talk, please add your questions to the chat. That is the way we do this. And the idea is that we have a few minutes at the end of each talk for questions, and every single talk starts, at a even 30-minute boundary so that people can join and jump between different streams. And with that, I'll get out of the way and leave the stage to Luca Sasselli, our first speaker.
So, hi everyone, good morning or good afternoon if you are in Asia or India. So my name is Luca Sasselli. I'm a senior design verification engineer in Qualcomm Ireland. And today I will present the research that I've done with Mehmet, Tukel and David Guthrie with the title Method for Early Performance Verification of Hardware Accelerated Embedded Processor System in RTL Simulation, which is quite a long title, but it gives you a little bit of an idea of what this is all about. So the agenda for the presentation will be pretty straightforward. I will start with a little bit of background, and I will define the problem that we're facing. I will then illustrate the solution that we propose and present a case study in which we use the proposed solution to address the issue. Finally, the result obtained and the conclusion. So let's start with the background. So the idea is that an hardware accelerated embedded processor system, it's a digital system in which an embedded CPU is aided in computation by a number of hardware resources. And this is done to increase the computational performance of the system without increasing the footprint, whether it's area or power. It's a common use strategy for things such as graphic, DSP, cryptography, and lately neural networks. But it's very generic, and you can use it for so much more. So the problem of these systems is that performance are kind of hard to estimate. That's because the performance depends not only on the hardware resources, but also on the software interacting with them, the architecture, how it's structured, the topology, the interconnection, and as usual, the physical implementation. So when designing such a system, usually the hardware-software co-design flow is followed. So starting from the system specification, usually an initial analysis is performed using metrics of existing components of previous generation products. And at some stage, the hardware and software requirements are finalized and hardware-software partitioning is defined. Then hardware and software can be co-designed concurrently. They will, in the end, meet again for hardware-software integration when they are mature enough to be co-simulated or integrated together. At this stage, the question is the system meeting the expected performances? So one of the issues that can occur is a performance bug. So the idea is since there is a long delay in terms of the design flow from when the architecture is analyzed to when the hardware and software are integrated and performance can be actually verified, the risk is that the good architectural choices have to be made very early on in the design cycle to meet performance. And if they are not, and the performance bug is introduced, they are just discovered late in the design cycle. So when it can be hard to address them. So a performance bug can be as simple as not achieving the required performance, but also exceeding the requirement can be as much of a problem because it means over-designing the system. So increased area footprint, increased power consumption, and a performance bug, if addressed, can lead to a certain amount of redesign and impact schedule. So the point is performance requirements should be verified as early as possible. So the proposed solution that we are going to present is to very simply actually addressing performance in the hardware design verification flow. So the idea is that in this way, the issues are caught first, earlier. So you don't have to wait to hardware software integration to address them, and you can have less of an impact on schedule. So the challenges in doing this, it's actually, first of all, having a performance extraction flow, something that can help you capture, analyze, and post-process the metrics extracted from your system. But also, since the software is not yet present at the design verification stage, developing a realistic software stimuli that is complex enough to basically model the behavior of the final real software application, but without the complexity of real software. So for the performance extraction, we propose a software-driven approach. So the idea is to measure the execution of the duration of critical sections of code. So how much a certain portion of code takes to execute from start to finish. So here's a small and very simple snippet of code, and I might be interested in knowing how long does the do-while loop take over multiple execution? What is the statistical behavior of this do-while loop in terms of execution time? So the method that we propose uses special macros. So the idea is that the macros are used to mark the critical section of code, and they expand to unique memory accesses to a location in the test bench that gets monitored by, in the location in memory that it's monitored by the test bench, sorry. So the idea is that we create a table between the unique memory access and the measurement, and the test bench simply detects the value and uses the association to basically perform the measurement using the simulation timestamp. So here's a simple implementation of the macro. So the idea is that it can operate in either two modes: a functional mode that is used for the actual software binary, in which the memory transaction is generated, and a non-functional mode that is used to extract the association between the unique value and the measurement from preprocessor output. So the flow goes a little bit as follows. So the source code is compiled and the binary is produced with the macro in functional mode. Also, the source code is pre-processed with the macro in non-functional mode, and the association between the unique memory transaction and the measurement is extracted. So in the test bench, a UVM monitor on a low delay memory, like for example, a tightly coupled memory, simply detects the accesses and uses the association to extract the measurements using the timestamp by simply monitoring the memory access events. So having such a framework, it's very useful because it allows to continuously monitor the impact of design changes on the system performance by, for example, adding automated checks during regressions, but also it can be used to, for example, just gather measurements and use a tool such Matplotlib to generate automated presentations that can be shared with stakeholders, just to keep them updated on the status of the project. Also, it's possible to simply post-process the data over multiple tests and have a more refined statistical analysis of the delay. So, for writing software stimuli, we proposed a framework that addressed one of the issues that we usually face when developing software for design verification, and that design verification tend to use very simple software structure and usually a very traditional software approach. And in this case, when you develop software using a traditional software approach, the structure of the code, it's linear with execution. And this can be a problem when interacting with multiple hardware resources that can basically operate asynchronously to the CPU. So the idea is that in real software, this is addressed by using a real-time operating system, but this can be kind of tricky to pull off in design verification time frame. So we propose as a trade-off using an event loop, basically. So an event loop is a software structure that it's basically composed by two elements. So an event loop and an event queue. So the idea is that the event queue stores events that have to be addressed by the execution of the program and gets populated by asynchronous requests from basically general events. So The idea is that every time something happens in the system that has to be addressed eventually, an event is added to the queue with an associated handler. So the event loop, it's simply the main loop of the program and pulls the event queue to basically check if a new event has to be addressed. And if an event is present, it calls the associated handler. So this way, it allows to delegate the execution later on.
Hello, Luca. You seem to have some kind of interruption here.
Interesting approaches that we were able to implement
Luca,
with this.
Please go back about 30 seconds because something you just froze.
Okay.
So, okay, yeah.
Oh, sorry.
Yeah, let's do this from the top. I think that's okay.
Okay. So, okay. So should I repeat the advantages of the event loop?
I think that's a good point to restart.
Okay, no worries. So the advantages of an event loop is that it allows to implement complex functionality with a simple software structure. One of the advantages that we also were able to exploit is that an event queue can basically be saturated with dummy events to simulate a CPU under heavy computational load without actually having to invent various scenarios to overload the CPU. It's less complex than a real-time operating system. It's very easy to integrate and can be implemented from scratch very quickly. And finally, it has a smaller memory footprint, so it leaves you like a wider margin to implement your program. So let me see if I can go. So sorry, now my computer is hanging. Okay. So the case study. So we use the proposed solution for a case study. We study the performance of an SoC subsystem that is composed by a number of hardware resources that are we going to call computational engines, or CE. The system had 3 of them. So each one was associated with a finite state machine, an FSM scheduler that basically was able to store multiple operations and execute it sequentially, a direct memory access engine, and an XI interface to access the outside world. So here's an overview of the subsystem in the larger SRC. So the data for the CEs, it's produced by a data provider, and it's communicated. This data is communicated to the subsystem using a shared memory, and flow control is provided by a number of IRQs. So the data flow goes a little bit as follows. So the data provider writes the data into the shared RAM and signals the presence of new data with an IRQ. The CPU basically reads the data using the DMA from the shared memory into one of the CEs, and the FSM takes over. So once the CE is no longer busy, the FSM starts the next operation without the CPU intervention. So the CPU has to only configure the FSM. So once the CE has completed the computation, alerts the CPU with an interrupt, and basically the data transfer is performed in the opposite direction. So the CPU programs the DMA to read data from the CE back into the RAM and notifies the data provider with an IRQ. So for our performance estimation, we were interested in a number of dataset processed per second. So datasets transferred into the system and processed out of the system each given second. So we started our analysis before the design of the FSM schedule could be completed. So we decided instead to perform our analysis using just the CPU. So this means an increased load for the CPU, and that basically every time an operation finishes, the CPU has to intervene to start the next one. So we use a previous generation SoC to model our interconnection delay, and we use a simple Gaussian model just to have a little bit of randomness in our experiments. we studied the performance using both the CPU to perform the data transfer and the DMA, just to estimate the impact of the DMA on the data transfer time. So we extracted 4 measurements: the dataset read time, which is the time that it takes to transfer data from the RAM into one of the CEs, the CE configuration time, which is very important since we don't have a scheduler, which is the time that it takes for the CPU to actually configure the operation in the CE, and the CE processing time, which is the time that it takes for the actual computational engine to process the data and give a result. And finally, the result write time, the time that it takes to read the data back into the RAM. So the results that we obtained are presented here. So they are normalized not to disclose any confidential information, so there is no unit of measurements, but they should still give you an idea of the relations, the ratios between them. So as expected, if you see in these 2 columns, we can compare the results with using only the CPU and using the DMA to drive the data transfer. And we can see that basically there is a tangible improvement in data transfer time, but there is no impact on the other 2 values. This is a kind of expected since they are uncorrelated. But one of the interesting things that we noticed is that the CE configuration time, so the time that it takes for the CPU to actually interact with the computational engines, it's kind of negligible with respect to the processing time. So in both scenarios, regardless of the measurements that we obtained, we realized that the throughput of the entire system was identical. So the DMA was providing an advantage in terms of data transfer time, but wasn't really affecting the throughput that much. So why it's not affecting performance? So the idea is that since we have 3 CEs in our system, so 3 computational engines, as long as we are able to feed enough data to them to basically keep them continuously busy, we are achieving optimal performance. So if we are transferring more data into our system, we are not improving our throughput. So we developed a very simple mathematical model that basically says, as long as we are able to transfer enough data to keep the CE busy, we're achieving optimal performance. And the optimal performance, it's the second formula. So it's simply the number of CEs divided by the time that it takes to configure them, plus the time that it takes to process the data. So with this in mind, we kind of started to see what are the things that are impacting our performance, because of course, both configuration and processing time impact our final throughput, but the configuration time, as mentioned, it's very negligible, while the processing time is one of the largest parameters. So since our condition to achieve optimal throughput depends on the data transfer, we kind of wanted to switch to a less conservative model for the interconnection delay in order to see if we were still able to meet performance under that condition. So we switched from a Gaussian model to a generalized extreme value distribution based delay. So generalized extreme value distribution, it's different from Gaussian, as you can see, but it's able to basically model an unbounded amount of delay with a very rare statistical incidence. And that's basically very similar to mimicking when an interconnection, a slave, it's basically busy because another master is accessing to it. So usually there is no collision in your system. It really depends on the system itself, but sometimes you will just find that your delay is very large because you're accessing something that is being used by someone else. So even with this model, we realized that we were achieving performances. So the consideration are that we developed a mathematical model to predict performance, and we realized that the configuration time of the CEs was actually impacting performance. And this is something that our initial architectural analysis kind of predicted. And it suggested and recommended adding the FSM to basically mitigate this. However, what the initial architecture analysis failed to predict is that while the configuration time impacts the final throughput, it's very, very small. So simply scaling the clock of the CEs, since the processing time, it's the bottleneck of the system, will give a much larger improvement in performance for the system. So in conclusion, we extracted the performance of a such system using the proposed method. Using the experimental data that we obtained, we developed a model of the performance, and we were able to prove that one of the hardware components that we were planning to develop to increase performance was actually providing a negligible improvement in performance. So this saved us NRE time. So thanks, everyone. If there are any questions, I think that I'm right on time.
Yeah, well, thank you very much. And as Luca said, now it's time for questions. We have 5 minutes or so, so please ask your questions in the chat. And I will read them out, or Luca will read them out, and we'll answer them. Okay. Yeah, I also see the chat. So anyway, I mean, I have one initial question here. I mean, this is a very interesting use case you presented, right? I mean, classic example of doing pre-silicon architecture to figure out, you know, what's important, what's not. But I mean, how did you actually know the software would be that insignificant? Because that would seem to depend quite heavily on just how well written that software is, right? I mean, you could imagine the software being a complete mess and taking a lot of time to set things up, or it could be, you know, reasonably well written. I mean, in this case, I guess it's pretty simple, but in a general case, I mean, the software driver for a piece of hardware running inside an operating system can incur a lot of overheads, right? So how do you make the judgment call about how do you model that driving software?
Yeah, that's a very good question. So what we basically did, unfortunately, we had to trim off a lot of our research just to get something that can fit in the 25 minutes format. But one of the things that we did that I briefly mentioned, it was to basically exploit the event loop based software to saturate the event queue with dumb events, just to basically pad out our software and delay the response time. So we started to basically kind of get a feeling of how much we can bloat our software execution until we see problems in our performance targets.
So you basically vary the execution time of the software somehow using the... Okay.
Correct. Yeah. So also, yeah, that was our main strategy. We also proved that we could tweak our software and simply obtain higher performance than what we initially obtained. So we collected a number of ways in which we could actually exceed performance with respect to what we use for the estimates, and we basically were able to get enough confidence to say, look, even if the software is this bad, you can still meet performance. Okay,
thanks. We have a question from Bas R to the next B. What is the difference between your method and traditional bus function models / traffic generators? Because, yeah, I agree. It seems to make a lot of sense to me that this looks like a traffic generator in the end, because you're just filing in transactions into your CE.
Yeah, that's true. The thing is, I think that a bus model, a bus functional model, and the traffic generator really don't capture the behavior of, correct me if I'm wrong, of the actual hardware resources in the system. So if you're trying to characterize functionally the entire system from CPU to the hardware resource processing data, bus is just one of the components of the performance. So I think that bus functional model, it's kind of needed if you need, if you need, for example, we used, as I mentioned, delays extracted from previous generation SoC to model our transaction delays. So if you have a more refined model for the bus, then you will have a more refined model for the final performance, but generally you're not capturing the hardware resources, like how much does it take for a certain peripheral on your bus interconnect to perform that operation, So this is more like a functional, like a system-wide functional approach to performance. So this is the difference, in my opinion.
Okay, so Bas, if you have any follow-up question, you can actually unmute yourself and say that now. Otherwise, I think we have time for one more question. So first of all, any follow-up from Bas Arts?
Thanks, Luca. We could probably take this offline in the virtual room. I think there's more room for a discussion on this. Thanks.
Sure, it will be a pleasure.
Any other questions for this talk? Last chance now. What was that? A hands up, or was it applause from Joachim?
was an applause.
Yeah. So with that, let's thank the speaker virtually. The classic, just type clap, clap, clap in Zoom, I think is the that we can do here.
Thanks everyone. I will mute myself and disable the camera.
And then we'll wait then it's time for Puneet Goel to present his talk. Well, once again, we'll start at 10 sharp European time, so that if anybody is jumping in from another session, and we still haven't seen the last speaker, so we'll see. So Puneet, you could start sharing your slides now, just to make sure that.
Am I audible and are my slides visible?
Yes.
Okay. So this is Puneet and I work at Coverify, where we are creating.
Wait one more minute until we start. Like, I just want to get this on the screen because as I said, I mean, let's start at the 10 hours. No, now we can start. Now it's 10:00 sharp. Okay.
All right.
Thank you.
Okay. So this is Puneet and I work at Coverify, where we're creating open source solutions for hardware verification. And today I'm going to talk about system level register verification and debug using open source tools. That is, we are primarily using embedded UVM. So this is the overview of the talk. I'll first introduce our vision of system level verification, and then I'll give an overview of embedded UVM. And by the way, embedded UVM was earlier known as VLang, but since there is a new language, a software language called VLang, so we had to change our name to embedded UVM. And in the end, I'm going to talk about some use cases. All these use cases are available on GitHub and then can be downloaded, compiled, and executed. So with the aberration in the Moore's law, like since 2005, the processor frequency hasn't been increasing. As a result, what's happening is there is people are bringing in FPGAs for what used to happen in software. So clearly, like earlier, there was a clear divide between hardware and software. Now that divide is fading. And for example, in the ISO or OSI layers for communication, earlier only the bottommost 2 layers were for hardware, and the upper 5 layers were usually done in software. But now kind of like at places a lot of hardware is getting used. Even in the application layer, we see hardware FPGA-based accelerators getting used. So as a result, system level verification and hardware software co-verification is becoming more and more important. So typically, like if you have an SoC FPGA, then you have FPGA cores available right on the embedded chip, along with, say, an ARM CPU. And so, you know, what earlier used to be a lot of times get done in custom hardware modules can now be programmed on FPGAs, and you can have a system ready very fast. But what we are going to talk about in this talk, is how do we verify this kind of systems where you have hardware and software interacting closely with each other. This is again slightly futuristic, but already started happening. So with you know, the CPU companies buying the respective FPGA companies. So what's happening is in the coming 2-3 years, you're going to have server systems, the server CPUs, which will have FPGA cores available as a resource. So today, when an application gets loaded on your desktop or on your server, then the application asks the operating system for memory to execute. It will need data memory as well as program memory, as well as it will need software libraries. But in near future, even when you load, for example, Microsoft Excel, a macro which is available, which you have enabled in the Microsoft Excel, say for AI calculations, that macro may ask the operating system to upload a particular bit configuration file in the FPGA cores. Okay, so this is the kind of complexity that will be there when we have the FPGAs on the processors that we run the applications on. So today, when you develop a hardware core, you know, this is a hardware IP. So you hand it over to an SoC engineer. So you hand over the RTL design as well as the UVM verification IP. And similarly, if you are developing a software application or a software library, then since you know, you could be working on a different platform, you could be developing it in Linux environment, while the system and integrator may be needing that library, say for Android. The CPU architecture could be different, and a lot of, you know, other differences could be there. So whenever a software library is made available to a system integrator, then what happens is you also hand off a software test suite. Okay, so just like you hand off a UVM VIP to the system, to the SoC integrator, which can be run on the system level, and that's the beauty of UVM, that module level test cases can also be run in the SoC integration level test bench. So the same way, the software library will need to be tested. You know, it's like this is how it is done today. So you deliver it to the system integrator, and you also deliver a software test suite. And then the system integrator will be able to find out whether the software library is compatible with his system configuration, and he'll then start using it. But what happens with SoC FPGA, where you are delivering a hardware module to a system integrator? So you deliver an RTL design, and probably it won't be the RTL design, it will be some form of bit file, okay, with information about what kind of FPGAs it is compatible with. And then if you deliver it along with a system Verilog UVM VIP, that VIP is of no use to the system integrator, okay, because he can't run it at the point of deployment. His point of deployment is a software, for example, the SoC FPGA. Okay, so he's not able to run the UVM test cases there, and he's not able to make sure that the hardware that has been delivered to him is configured properly, it's mapped properly on the FPGA, and it's working the way it should work. A similar problem is faced by validation engineers today, where a chip comes back from the fab, and the first thing a validation engineer does is he boots up the CPU. Okay, he brings up the CPU because every SoC is going to have some kind of CPU system. So he'll bring up CPU. He'll probably bring up either Android or Linux on top of it, and then he needs to do the actual verification, which is basically like CPU is usually standard. So most of the times the bring up is not very difficult, but then comes the need to test the modules. That's what your IP is. Okay, so for example, PCI module, USB module. So the need is to test those modules and make sure that your software drivers are working properly. So that's the time where validation engineer wants to have some kind of understanding with the verification team. He wants to run the same test cases which the verification team was running, but he's not able to do those because those test cases are not usable at the point of deployment. Okay, so the idea is how can we enable hardware software co-verification? Another useful perspective from what is happening is like you all know about RISC-V and the open source hardware movement. So typically all the open source projects are posted on GitHub or GitLab or some other public hosting platform. So when so the difference is in a closed source environment, you have a very well organized and systematized team, so they know what the flow is, and they are able to work, in close coordination with each other. They work on the same tools, for example. But in an open source environment, you have developers from across the world. So you have universities, you have institutes, you have individuals, and they want to contribute to, say, to RISC-V open source development. And one of them is, say, fixing a bug or creating a feature, and he creates a pull request. And what happens is, as soon as the pull request is there, GitHub, usually that's what happens on the software projects. You want to trigger automatic testing using something like continuous integration. So you have Circle CI or Travis and other platforms which will automatically run test cases for open source software. Okay, so and if any of the test cases fail, then the pull request is sent back to the developer, and he needs to fix the pull request that he is making, and he needs to make sure that all the test cases are passing. Only then the pull request will be available for review. Okay, now the point here is, unless you have the test or the verification environment running on the cloud, and running on the cloud means it also has to be open source. Okay, also from the point of view that if it is closed source, then all the developers across the world who are kind of contributing to this project, say to RISC-V, they need to have the same version and same vendor to procure the tools from. So one of them cannot be using System Verilog compiler or simulator from vendor A, and another one from vendor B. It has to be same, because and the same tool needs to be used for continuous integration. Otherwise, if a test case is failing, there is no way the developer can have the same test case run in his local development environment. It fails on the cloud, he needs to replicate the failure in his local development environment. Okay. So from here we come to embedded UVM overview. It's a complete port of IEEE UVM, and we have managed to port the latest 2020 release of IEEE UVM. It natively compiles. That means it can run on Microsoft Windows, it can run on Linux, it can run on Android, and it can run on most of the CPU architectures. And since it will create binaries for you, it's also is having portable stimulus. So the stimulus it's going to create in your Linux environment will be same as the stimulus it will create if you are running it on an SoC, and that SoC may be using Android. So it's going to create the same sequences. It's multi-core empowered, so it's the only version of UVM which has multi-core. It's a multi-core port of UVM. It's systems programming enabled. That means it's ABI compatible with C, C++, meaning thereby if you have a pointer in C++, you can directly see without any underlying DPI layer or anything. You can directly see it in embedded UVM. And if you have some randomized data in embedded UVM, your C, C++ libraries are going to see it directly at the level of pointer. So you can pass a pointer to the library, and it's going to see that. It's completely open source. It's built on top of unlike System Verilog, which is built on top of RTL. It's a bottom-down architecture. It's a top-down architecture where we use D programming language, and on top of D programming language, we create hardware, verification and hardware libraries, and then we create embedded UVM. And then if it needs to integrate with RTL, then we have DPI, VPI, and VHPI interfaces. But yeah, I mean, usually people think VPI is going to, or PLI is going to make the simulation slow. It doesn't become slow because we run the test bench on a separate thread, and the RTL simulation is running on a separate thread. It's fiercely native data types. What does it mean? If you have an int or say you have a bit vector, then if you are making it random, for example, the random keyword over here is not going to add to the memory footprint of the variable. Integers are going to be 32-bit. U-bit vector, which is 12-bit long, is going to be 16-bit because you have to align at the boundaries, at the byte boundaries. It's we support all the constraints that System Verilog supports. So we can even we also support, for example, things which normally open source doesn't support. For example, if you have an array of objects or array of components, and then you are having constraints which are relating one sequence to another sequence, and multiple UVM objects are getting related through the elements inside those objects are getting related through common constraints. So all that kind of thing is supported. All right. Then we also have UVM rich layer library. We have a complete port, including the rich layer sequences. And so typically, this is common. Like this is how it happens in System Verilog. This is how it happens in embedded UVM. So we have we also have a utility to create reg models. So our reg models are slightly different from System Verilog reg models. Basically, the syntactical small differences, but we have those utilities ported to for working with embedded UVM. Okay, so coming to the last section, I'm going to talk about 3 different utilities or 3 different applications that would be useful, and that generally are not there. Some of those are some companies, for example, QEMU reg layer. So there'll be some companies who have homegrown tools for doing it, but there's no open source project. There wasn't any open source project because System Verilog being closed source, so open source movement for verification hasn't picked up. But with embedded UVM, we are creating this kind of open source projects. So first is interactive register debug. So what happens is, like in this project, we have an Excel spreadsheet. This is a normal Excel spreadsheet. If like you could be using the register description language to put your register specification, or you could be using Microsoft Excel to document your register description. So and usually they are interoperable. Like if you have RDL, then there'll be tools to create comma separated file for you, which can be uploaded in an Excel sheet. Okay, so in this particular utility, what we do is we have the register specification in Microsoft Excel, and so the register names, the register addresses, the field names, and the bits. Okay, all those and the attributes to the bits, like whether it's read only, read write, and so on. So those are available in the Excel sheet. And what we do is we run a simulation on a Linux machine. It's the RTL simulation. Like if you we have uploaded this project on GitHub. So if you download it, we use Icarus Verilog simulator, but any commercial RTL simulator can be used. So the simulation then talks with the Excel sheet, okay, using TCP/IP interface. And on that TCP/IP interface, we send something we call reg packets. So we send, for example, from the Excel sheet, when we click on a particular cell and we have a macro associated with it. So all that macro programming has been done in Python. So Microsoft Excel also has a Python plugin now. So as soon as that particular button or cell is accessed, so it triggers a packet on the TCP/IP interface, which is received by the embedded UVM environment, and then it is interpreted there, whether it's a read command or a write command, and depending on what kind of information has come over the TCP/IP interface, we perform the particular access on the registers on the simulation which is running in as a you can say server simulation, or as a you have like the Excel sheet is the client and this is the server. The simulation becomes the server. Okay. So we defined a struct. This is all D language, and in the D language we have aligned it on byte boundary, and we send the command to on the TCP/IP interface, and there it's interpreted, and the particular simulation step is performed. The result of the register access comes back to the Excel sheet. Okay. Now this is very useful for designers. Like till now, you do verification, you do register level verification, and that register level verification is very nice in register package of UVM. Okay, but it's not interactive. So you write one sequence of registers, and if you want to change it, you'll have to recompile your test case. Okay, so here we make it interactive. So the simulation actually waits for the command, and we do it through a virtual sequence. Okay, the virtual sequence is written in embedded UVM, and it waits on the TCP/IP interface to receive a command. And then it will interpret, it will create a real sequence, send it to adapter, and then it will interact with the RTL simulation through PLI, and the result will come back to Excel sheet. The next is a co-verification environment between QEMU and embedded UVM. So then the DUT is running again on an RTL simulator, which could be open source Icarus Verilog simulator. And it's very similar in nature, but since QEMU and the simulation could be running on the same server, both could be running on the same host. So instead of using TCP/IP channel for communication between QEMU and the simulation, we use Linux FIFOs. Okay, again the same thing. We use the same register read-write packet format, and then so this is typically how it is done on the QEMU side. So if the QEMU is using the normal software drivers, then it will perform normal software read-write through these macros. But if the QEMU is trying to co-simulate with Verilog simulation, then it will send the packet it will call a function which will ultimately send the packet through Linux FIFOs to the simulation, and it will wait for the result, and that result will get reflected. So it's kind of transparent, like COSIM reg read will provide it whatever has been read from the register. Okay, so you have a simulation and you have QEMU for hardware emulation or for software emulation, and both of them can co-simulate using this environment. This is again available on GitHub. I'll share the repository with you later. So finally, we come to the third project, and here we have an SoC FPGA environment. We have design mapped on FPGA, and since it's SoC FPGA, we also have an ARM processor like on Cyclone 5 or UltraScale Zinc. So you have ARM processors. So we have embedded UVM running on this ARM processor directly here. So this SoC FPGA doesn't need to communicate with any simulation on any server. So it's very easy to set up. Like you just create a test bench on your host machine, push it to SoC FPGA, it will run there, it will create the stimulus on that ARM processor, it will solve the constraints there, and it will push the stimulus to the FPGA, and it will get the results back. And all the UVM monitor, everything is running here. And it runs very fast because there is no software, there's no Verilog or HDL simulator involved. So only the test bench is executing. Excuse me. So this is what gets enabled. Like in your UVM test bench, you will be able to directly make Linux operating system calls. So here, for example, I'm enabling the access to the FPGA, which gets enabled as a peripheral through a generic input-output device, okay, on Linux. So I'm reading it for read writes. I'm just kind of mapping it to the virtual memory, and then I can so you can see the mix here. This portion is totally software. It's system level software, and this portion is UVM, where we are having a final phase. Like at the time of tearing down the test bench, you want to unmap so that your virtual memory gets freed up. So this is what makes the when we were looking at the slides earlier. So if you give a system Verilog VIP to the system integrator, he has no use of it. He doesn't even have because he's a software engineer, he doesn't have a system Verilog simulator. And even if he has that, there's no way he can test it on the FPGA. So it can't be tested. Your design, which is at the point of deployment, it cannot be tested. With embedded UVM, you can provide the same stimulus to the RTL simulation, and the same stimulus then you can apply to your FPGA design. So meaning ultimately it also at module level, since FPGA sizes are also growing, so you can even create mini emulation platforms. And when hardware accelerators on the mainstream processors, the server end processors become mainstreamed, so then you will have the ability to put your design on the FPGA, run embedded UVM on the processor, and directly do the testing at FPGA level. So your desktop server or your simulation server, it becomes an emulation environment. Okay, so we are on GitHub. You are welcome to fork it. So all these 3 projects are there. We also have a RISC-V DV ported to RISC-V, and this is something we are very excited about because we are also creating a multi-core version of RISC-V, which runs RISC-V pattern generator, which runs much faster than any commercial tool. I'm just going to show you some code here. Like this is the level of difficult constraints that we are able to solve. So all these constraints we have written for. And another thing you will be able to notice is it's very close to, syntax-wise, it's very close to system Verilog. Okay, so all kinds of constraints, everything. So this constraints, this block of constraints starts here. It goes up to here. And this is directly ported from RISC-V. So we haven't changed any constraints. Everything that was there in system Verilog platform or RISC-V DV project for RISC-V verification in system Verilog, everything is line by line ported into embedded UVM. Okay. And thanks to multi-core, it runs faster.
Okay, so the thank you. This was a really good talk. I guess we have time for 1 or 2 short questions, so please send them over the chat. Okay, first of all, do you have any plans to support for PCI Express-based FPGAs?
Yeah, actually, what happens is, so whenever you have an FPGA, you will have a software interface which will mostly be memory mapped. So irrespective of what kind of software interface you have, you'll be able to. But yeah, I mean, we don't have any standard drivers for PCI-based accelerators today. We have only tested for SoC FPGAs. We have tested for Cyclone 5, for UltraScale Zinc, and for the normal Zinc.
Okay, so I have another question myself. So what you basically started with here is a system Verilog test bed with UVM, right?
I mean, we don't directly use system Verilog. It has to be manually ported because, you know, system Verilog
okay.
is,
so you're actually writing the test cases in D. I thought you took existing test cases and just translated into D.
Yes, but translation is very user-friendly. I mean, doesn't take too much time. Like the whole RISC-V DB environment that is there in system Verilog, we took 4 weeks to translate it. It's about 15,000 lines of code.
Okay. Okay, please ask more questions in the chat. I have one more. When you talk about the QEMU integration, I didn't quite understand what you were doing, right? Were you modifying the target software, or were you just modifying the model? Because to me, it would seem natural to run the actual software on QEMU as it would run on hardware, and then it would just say that this piece of the memory map, we just throw these operations over to the other side. I mean, that's how I would do it in my simulator.
Okay, so typically we are targeting hardware driver developers. So when they are developing software for hardware and the chip is not available yet, then QEMU integration makes it possible for them to run the hardware driver on QEMU and all the register, because normally all the communication between the software and hardware is through memory mapped interfaces. So the communication, whatever needs to happen with the hardware, will happen with the simulation running on embedded UVM.
Okay, so I think we have many more questions now in the chat. I think we'll have to take them in the virtual rooms later on, but just to read them out, I mean, how does this compare to UVM System C? I think that's a good thing to answer. And do you have some kind of UVM to embedded UVM porting guide?
We have a complete, like System C UVM is a part port of System Verilog UVM. We have a line-by-line compatibility with System Verilog UVM. So any command that is there in System Verilog UVM, you will be able to find in this code. So we don't need to really have a manual, because everything is the same commands, same classes, and every kind of constraints, everything is possible. System C UVM doesn't have a good constraint solver. You have Crave, which normally is not well supported these days. Our constraint solver is world class. We are able to run RISC-V DB in embedded UVM without multicore. We are able to run it at the same speed as System Verilog. And with multicore, we are able to beat System Verilog simulations.
Okay, thank you very much. It's time for the next speaker. So we have, let's see, we have Svetlomir, Hristozkov. Yeah, Graphcore. So Puneet, yeah, please mute yourself, and Svet, could you please start sharing your screen so we can see if that works?
Right, 1 sec. Could you stop sharing, please, so I can share?
Puneet, could you stop your share?
Thank you. 1 sec. There we go. Hopefully you can all see this now.
Yes.
Okay, so before we start, I just want to say I've got 3 demos on here. I very much doubt that I'll have time to do all of them. So at best, I'll skim over them, but I have pre-recorded them and I've embedded links to them. So if one person goes and watches them, I'll consider that a success. That said, my name is Svet. I've worked at Graphcore for 4.5 years now.
Could you please share full screen? Otherwise, it's
is it not full screen?
No, we're only
it was.
PowerPoint editing mode. Or that's better. Thanks. No,
okay.
Now it's bad again.
It was full screen on my screen.
This looks good.
Yep. Okay. Right. So my name is Svet. I've been working at Graphcore for 4.5 years, and for those, hopefully you have maybe heard of Graphcore, but for those of you who haven't, Graphcore designs accelerators for machine intelligence and AI to do both training and inference workloads. And I've been working as part of the verification team for the past 4.5 years, like I said, leading a small team focusing mostly on SoC verification, so interfacing to the outside world, etc., etc. But I have a personally, I do have a very strong interest in methodology workflows, and that's kind of what I'll be talking about today. The first thing I want to talk about is the obvious reference in the title of the talk, No Country for Old Men. So the reference here is twofold. One, if you haven't seen the movie, it's really good. I recommend it. And secondly, it's about a getaway, and that's what we do in verification. Will never be done. Will never be properly done to our satisfaction. So it's about getting away with just what we need to do, and just with the amount of resources that we have. And there's also a little bit of a reference to, I think, in my opinion, that the fact that we as an industry have maybe failed to keep in touch with all the recent advancements in tech in particular. So have we kept pace with innovation? Like I alluded to, in my opinion and in Graphcore's opinion, verification is all about resources. It's about engineering resource, it's about compute resources, it's about time, really. And I've taken here a little plot from the Wilson Research Group from 2020, just illustrating how we spend our time as verification engineers. So doing mostly debug, creating tests, running tests, and I'm guilty of sometimes running a sim and maybe waiting for it to finish rather than switch context. And that's maybe an inefficiency that we can maybe help address a little bit, and similarly address the test bench developability analysis, all of this. So that's kind of what I'll be talking about today. So obviously, one of the things we can do is to address compute time is to buy more compute. However, so this is roughly what we tell management whenever we request new compute. And it's roughly true as well in our observations. So our compute requirements will generally go up towards the tape out, but they will never ever go down. So they'll stay flat for a bit, maybe around the tape out time, and then they'll start going up again. And that's because we incorporate more and more things in CI, and we need to analyze how we look at this better. So is there anything else we could do? So let's look at our flows. So this is again taken from a paper, and it's illustrating the typical metric-driven flow that we're all familiar with. So this works. We have that iterative flow between regression testing, where we have a test bench, we collect some metrics, our verification plan, and our verification report. And typically, we'll maybe write our verification plan, set up a test bench, write some stimulus, collect some coverage, map it to a verification plan, look at the coverage and the results, maybe change our constraints and iterate over that loop. And then between doing this, we need to update multiple documents and files. We need to update our test bench and regression environments. We need to update our verification plans. We need to probably run a third party to produce a report to put the two together. So all of this is a potential drawback to our efficiency. So is there anything we can do about this? What we're proposing is we keep the basics, the fundamentals of this the same, but if we do a few small little adjustments and maybe use slightly different technologies, we can possibly enable new workflows and possibly enable some new tooling, which will make our runs easier to analyze, faster to analyze, and even get some extra performance out of our runs compared with what we refer to as a standard methodology, really. So I'll be talking about all of these things here. So the ones I've listed in. Right, so this is a very rudimentary diagram of what our flow of Graphcore is, and we've based it though on a single source, golden source coverage model written up in Python. The choice of Python is really arbitrary. It's really because of the expressiveness of the language. It's not for any other real reason, really. And it allows us to interface to loads of different technologies very easily. So we'll read in Python, we'll read in our architectural specification. So that could be IPExec, could be XML, could be any machine readable format, could be anything you use internally, it doesn't matter. And we'll use that to produce and compile our verification plan here. But we'll also feed this in from the simulator. So this is getting data here into the Python, and the Python then uploads it into an SQL database, a relational, very quick SQL database that we can then use to build loads of tools on top of. And I'll argue that the tools we've been able to build are probably come as a separate product really to any EDA offerings. So that's an advantage, and they probably boost our efficiency. And I'll try to illustrate why. Right, so let's get into the crux of things. So in terms of new flows, what could we do? So the first thing I'm going to talk about is developing coverage plans and coverage far ahead of any test bench and RTL work. And this is why I have my first demo. So I've put in parts of the code for the demo in this slide. I will quickly switch screens if that's okay. So just hopefully you can now see my code window here, and it's remotely readable. Please let me know if it's not.
Yes, we can see the code.
Yep, great. So what I've done is I've defined a little specification here, just completely arbitrary in XML. So I've called it the Svet interface. Yeah, because I'm, yeah, never mind. Yeah, who names interfaces after themselves? But hey, there we go. I've got a header, which has got a bunch of fields. So it's got 4 fields called command, address, chip select, and reserved, just arbitrarily. Just to make things interesting, some of those fields have an enumeration type defined for them. So for example, for the command, I can have a write, a read, or a sync command, and just because I had an extra value left over, I have a high command as well. And I've illustrated the values for each of those. And then finally, I have a 32-bit payload. So what I've done is I've written some coverage for this, and this is it right here. So this is my cover point. What I want to draw your attention to is firstly this motivation here, which is what will go into my verification plan. It should talk about what the cover point is, why is it necessary, how is the coverage going to be collected, etc., etc., etc. And then this is the actual cover point. This is all the code that I need to write for this. So this is creating a cross. A thing to note here, there's a slight difference in nomenclature compared to the LRM. So what the LRM might refer to as a cover point, we refer to as an axis internally, and what the LRM might refer to as a cover point, as a cross, we refer to as a cover point here, but otherwise entirely the same. So literally, I iterate over this here in XPath, in Python XPath. So this is literally 4 lines of code. Take all the information in, and that will generate a nice verification plan for this. And I will just run this now real quick, and hopefully it will all work, because demos never go wrong. So what I'm running here is our internal wrapper script, which is build. I'm giving it a top argument of DVCon demo, and then I'm telling it run it in the documentation platform and run it in the test chip environment. That's literally it. And hopefully this will give me a nice PDF documentation that I can go have a look at and review later on. Right, so it's running Sphinx, so it produces a LaTeX output. And so if I go here, there we go. So I have a little PDF. So if I open this, come on now. So there's my document. Ordinarily here, I would have a lot more in this context section, I would have written up a verification plan. I would have written up what my test bench looks like. I would have written how I drive it, what my constraints are going to be, what my test cases are going to be. But on top of that, I will have those cover points that I just talked about, and I'm just going to show this. So I get a cover point section with a unique identifier with a hyperlink embedded in there. I can view this as an HTML page as well. And this is what it looks like. So I've got my full coverage here, documentation generated. I've got a little bit of a code expert here, which is meant to indicate if I've got any illegals or, you know, don't cares really defined, and where I can find this in my source code. And eventually, after I've got some coverage running, and we'll do that in the second part of my demo, I'll be able to also annotate this with some coverage. And this is a very, very easy thing to use as a sign-off metric, as a review in a review process. So that's that demo done. I have a more detailed version of this demo in the link if you want to have a look at it. And I'll just move back to my slides. So hopefully that's okay. So I've done this now. Right, as the next bit, what can we do to work faster? So typically, I remember when I used to work in an entirely UVM system Verilog environment, and a lot of my time was spent waiting on simulations, waiting on results, then looking at the results, then updating, recompiling everything again, running it again. And then on top of that, you're limited by the number of licenses you've got. So there's always going to be a limit, right? No one's got infinite licenses, or maybe someone does, I don't know. So what can we do to address this? So turns out that all we need to do is to make a small leap and just not do stimulus in UVM. This is at least our solution to that particular problem. So if we move all our good bits or constraint random stimulus, you can even move your entire test bench. It could be in C++, could be in Python, could be anywhere really, doesn't matter. If you move that to a different programming language, you no longer need a license. So what you can do instead is you can run your stimulus, inject it into your architectural model, use your architectural model to collect coverage, which is based in Python, like we just saw. And I'm just going to show you the sample methods in a second of how that works. So we can do this offline, essentially, without a simulator whatsoever. And it's going to be pretty much instant, as we'll see in a second. And I can work on my constraints in a very much quicker iterative loops. How we then use that in simulation? Well, we write out the stimulus. In our case, we do it in an XML format. It doesn't have to be. You can just store it in any way you want. You can even generate it online, as long as it's the same seed. You then replay it on your device under test. You have a monitor, which you'll then call over the C DPI into your C architecture model. And then the final step into the Python collection is the same. And to do that, we use Boost Python as the interface there. It could be Python, it could be a number of other solutions as well. How does that compare to conventional UVM? Really, it's quite the same if you think about it. Only you move bits of this here into a different language. That's literally all you do. And that hopefully, I'll show you, enables a really powerful workflow. So stimulus and constraint random is done offline. So we have a little test generation platform we've built in Python. This is a topic of a different talk altogether, I think. So I'll not go into any details on this. And that's it. And so this is how it works in practice. So on a more technical level, how it actually works. So you have the device under test that does some transformation here on the next packet and produces a Y packet. Otherwise, you notice the test bench looks very similar. So you have a bus monitor thing that will send stuff to subscribers. The subscribers are in your DOT. In fact, our modeling, C++ modeling here, actually still uses TLM infrastructure, just written out in C++. Otherwise, entirely the same as UVM. And on top of that, it will just bridges over to Python where we can collect coverage. We still have scoreboards, all of that good stuff. So that's unchanged. The only difference is we first replay our stimulus in the test gen platform. We collect coverage on that. We develop our constraints there. So that is hundreds of times faster, quite literally. So let's get onto the demo. So I've embedded the link here. So this is a longer demo. So I'll really skim over this because I won't have time to do it fully. But I will switch over to my code again. Okay. Was that not working? Share. Is that sharing my screen now? Hopefully it is.
Yes, we can see your a PDF. Now we see some consoles and text and the PDF in the corner.
Yep. So that's from the old demo. So going back, so what I've done is I've set up, so I have my coverage here that we had a look at. Let's have a look at how the sample method looks like. So this is the equivalent of a system Verilog cover group sample method. Looks very similar. You can have loads of complexity in here, but I've just had a really simple one. So this just gets a Python dictionary. You sample that and you increment the count you have for this. That's literally it. That simple. I've set up a little Python test bench to run this, and this is my test bench here. What do I do in this? So I set up my connection to the database. I create my coverage instance, my coverage hierarchy. I then set up a connection to the database with that hierarchy and set up coverage callbacks. This is used to bridge C++ to Python eventually when we do have it. And I just generate some packets here, and I can show you the test generator that I have for this. It's again quite simple. So won't spend any details here. It's just a Python generated creating random stuff with a distribution here of all zeros, with equal weights of all zeros, all ones, bit set, bit clear, random, etc. So it's going to produce 1,000 packets, and we're going to collect coverage on this. That's literally it. So I will now run this, and hopefully I have this in my history here. Right, there we go. That's it. So I changed my platform to be the Python platform, and I just give it that script of my Python test bench, and that's now running coverage. My coverage is done. So I will now show you our integrated dashboard for looking at coverage. So switching screens again, so hopefully not too destructive. So there we go. So I've got my sims here. I've already taken the liberty of pre-filtering this for myself only, but I can really see on here all the work everyone's doing. So I can click on my name here. I open that regression. I can see the test. And you'll notice that these messages here are exactly the same. So this is all my messages have gone into the database. But on top of that, I've got a nice little coverage report just here. And this is what we call a coverage donut. So the outermost, the innermost ring of really an onion really is my full coverage container. So I've got 4% coverage on the coverage I did define. I then have a tabulated view of all the cover points that I do have. So let's have a look at one of them. So there's my first cover point that I defined. I get a standard tabular view with all my axes defined here. I can filter on those. So I can say, address is 5 and reserve is 13. So that works quite quickly. So really quick filtering. I've got what we call a pivot table row view, which allows you to focus on particular axes that you're looking for. So something like this. So I can look at the cross of address and command only and ignore the other two for now. So this is just in terms of analysis and how we can improve analysis. And I'll cut it here. There's loads more stuff that I can show here, but I really want to cut it here because I'm doing poorly for time. So just going back to my PDF deck, this is a 10-minute demo, so feel free to have a look at it if you want to. So I also demonstrate in this demo here how we actually replace what I just did, where I just generated Pythons and packet and I drove the coverage in Python. It's a one-line code change to drive the packets in C++ instead.
Is it right now you're showing your PowerPoint again?
Yes, I'm back in PowerPoint, yes. Correct.
Yeah, but I mean, we still see your PowerPoint editing mode. We don't see the full screen.
Oh, right. Okay, sorry. Hopefully that's better.
Yeah, this is better.
Yeah, so it's a one-line change to swap back to a full C++ architectural model where we actually inject the Pythons, the packets in our reference model instead of just doing this. Whoopsie, I do not want to play this now. We can do unit testing. So Python does support a very large ecosystem of unit testing. So that's great. I know we can do that in SV unit or SVA unit, but again, you have the extra EDA licensing requirements. It's a bit slower to develop. And I have a demo which I've uploaded. It's only 2 minutes. I'm not going to do it now. Feel free to have a look at it. It's really that easy, showing how we can do stuff. So I'm going to skip this now. what other tools can we do? Since we control all the coverage infrastructure, we're not reliant on an EDA tool to do this. So we have all the full backend for the coverage database. We can do stuff like coverage printing. And what is coverage printing? So it's a way of using past data to speed up our work. So just anecdotally, if the more coverage we have, the bigger penalty we pay in terms of runtime. And the larger our cover points are, again, the bigger the penalty. And really the penalty stems from the fact that it takes time for the actual tool to locate the correct bin in the database that it's using. Additionally, on top of this gets worse with time. So the further we're into a project we are, the harder it gets for us to hit cover points. This is a well-known fact. So constraint random works really well at the start, but the closer you get to full coverage, the worse it gets. So how can we use old data to kind of counteract this this kind of effect? So what we've done is called coverage printing. So we'll use a very short regression. So we noticed that we hit a large proportion of cover points to 100%. So they're a lot easier to hit with very few tests. So we'll do that. We'll run a short regression. We'll have a look at all the cover points we've hit to 100%. And then we'll run a longer regression, pruning away all the cover points that we know are easy to hit. So in this demo here, I've got an example where I've run a short regression. These here are the automated results produced from that regression. So I hit nearly 45% of my cover points to 100%. I hit 60% of all bins, but really what I'm interested in is those 45% of cover points hit to 100%. I'll then use those to prune away in my next regression the cover points that I know are easy to hit, and instead maybe run more seeds to try and hit the cover points that are difficult to hit. So with doing that, I've run the same regression twice, once with pruning, once without pruning. And when I use pruning, my runtime goes down by 8 hours. Now my coverage will also go down because I have a number of cover points that are no longer collecting coverage at all. But really, I can argue that this coverage here is just as meaningful as this one here. And instead, I can use the extra 8 hours of compute time to run more seeds. So that is kind of going to get better the further into a project you are. So it's going to counteract that diminishing return. We can do multi-threading since we do all our coverage processing. So we have a front-end Python to define our coverage, but we have back-end C++. So it's quite easy to actually set up a multi-threaded run, which I think EDA vendors have had a notoriously difficult time with. And this here, so we're kind of using the fact that what normally happens in an EDA simulator is you run a bit of simulation, you capture a packet, you then go and collect it, and that collection process, literally incrementing the number of hits in a particular bin, takes a long time. So what we do is we offset this particular box here in a separate thread. So every time we have coverage processing to take place, we do that in a separate thread. And this is the result of a real actual test that we can run. So this is a test we use. If I run it in a single thread, it gets 320 seconds runtime. My processor load average is about 1. If I use a double thread, you'll notice now I have more than 100% utilization for my CPU core. And that's really because I'm using 2 CPU cores, really. But my latency, so my time to result is a lot lower. So I have to wait around less to get my final result. Of course, there's going to be a limit to how much of an improvement you can make, but especially for, and that comes from Amdahl's law, really. But you can get a bit of improvement, especially with very coverage intense test benches. The total compute time, however, is going to be identical. This is not a performance improvement. Well, in terms of analysis, I showed you the coverage donut and the pivot table pivot row view. There's a whole load of other extra stuff I can talk about here. So a ton of tools were built around this. An interesting one is this coverage saturation thing. So this is a real report. All I've done is I've renamed our test names to A to K. So these are real test names run on the real test bench. I've just renamed them to obfuscate their names. And what that gives you is what sort of coverage does each test give you. And this way you can optimize your CI runs, figure out how many seats you need to run for each individual test. So for example, you can see that this one here is probably quite good. This one here still goes linearly, so it's probably worth running some more seats. these ones here probably already kind of saturated, so I don't need to go have a look at those constraints there, or I don't really need to run any more seeds of them because they're not giving me any extra incremental coverage. So bang for buck, they're not worth it anymore. So the pros and cons of this, very massive learning curve. So it's not UVM standard. There's multiple programming languages. So there's DPI involved, there's C++ involved, there's Python involved. So that's not easy to pick up sometimes. It's not in EDA. Reliance, so this is both pro and a con. So it's definitely a pro because we can run all our tests on all tools, on all EDA simulators for the same seed. We're always going to get the same result. It works. We're always going to get the same result. It's reproducible. It's very easy for us to switch simulators and only look at simulator performance and nothing else. So it's EDA simulators become a lot less sticky. So it's great from that perspective, but we do have to maintain it. However, it's quite easy to pick up by software engineers who are quite comfortable with C++ and Python. So we have done that in the past. In crunch times, we have actually commissioned software engineers from our software teams. And it's very customizable, so we can build any tool we want to. And I'd argue, especially in terms of coverage merge, coverage collection, we do get a lot better performance compared really with the big tree. So I don't really have any current data for this, and it's very difficult to benchmark this. It's all anecdotal. So it's just my word for this, really. But
okay.
I'd love to have a good data for this. And that's me done.
Perfect. So we have time for maybe one short question here before we need to go off to the panel.
Yeah.
Do we have any? Ah, perfect. Are there any questions on the chat? In that case, I have a short question in the meantime. When you say C++ for your architect simulator, is that actually system C? Because you mentioned TLM, or is it just home bake C++ framework?
It is literally a home-baked C++ framework. It's a lot more, it's very much lighter weight than System C. So it's something we built in-house that it's really quick to run. So we've benchmarked it, it's quicker. It's all about performance. We've really focused a lot on performance. Yeah. I'm afraid it's not available on GitHub. I just saw the question. I can share the demo code on GitHub if that's helpful, but it's also visible. It won't be runnable on its own, and there's some base classes involved there. I would really love to be able to open source this, but that's a discussion to be had separately, I think, internally. Yeah, so it's been a long development. I'd really love to share
it's still good, right? The fact that you actually share how you do things like this is still interesting.
Yeah.
Yeah.
Sorry. Yeah.
Yeah, but please, if you have a very short answer to that one, because otherwise we need to jump to the next session.
Okay, so yes, we can capture coverage from assertions as well. Yes, and also structural coverage. So, so there's two ways you can do this. One is via VPI. That works. Another way is via UCDB, but that makes it so EDA vendors, understandably, I think, there's a standard. I think the standard's not particularly good, I'm afraid, UCDB. So there's an API, but how each of the vendors interpret that standard is different. So you will need a separate interface for each vendor if you use the UCDB standard to collect coverage from assertions. We have done that. So we do collect functional coverage from the vendors, and then we put it into our SQL database.
Okay.
But you can also do that via VPI.
Yeah, sorry to cut everybody short here, but we're out of time, and we have a panel next on the schedule. And after that, we have the sponsor sessions, the poster session, and more sponsor sessions. I think we can grab some lunch during the sponsor sessions idea for the rest of the day. And as Asma noted in the chat, please click on the SurveyMonkey link to go and vote for the best paper award, because now we're actually rolling through the papers. It's time to vote for these. So thank you everybody for joining the session today. I think these were 3 really interesting papers. I really enjoyed it myself. But yeah, let's shut down this session and head over to look at the next panel.
Cheers, thank you.
Thank you.